All right, everybody. So welcome back to office hours. Thank you guys for coming. The day after your exam, it shows that you guys are on top of it and you guys really care about the class. So I'm happy that you guys are here. And I also hope that you guys are happy with your exam one grades. I've already gotten a lot of emails since the scores were released like an hour ago. And a lot of the emails are saying like, oh, I put SP caret 2 when you were like trying to say SP2. And that is totally fine, even though they marked off, like the computer marked off. So if that's an issue for you, like, don't worry, you'll probably get your points back. Just fill out that grade request form and send it to Dr. Peterson, and that should be good. Overall, I saw the test. I didn't think it was too crazy. I think there was one kind of question with basicity that I thought was pretty challenging towards the end, but other than that, it was pretty fair. I think we prepped for it good enough. Do you guys have any feedback that you guys want to give to me that you think would be better for your next exam? All right. Someone? Yep.
Yeah, so I don't know if it's just me, but for some strange reason, the practice exam on Canvas was much harder than the written practice exams.
Okay. And so you thought that the practice stuff was harder than your real stuff. Okay, basically. That's a good problem to have if that's true.
Yeah, so like maybe in the future, can we try a practice exam on Canvas since from my perspective, they tend to be harder?
Gotcha. Instead of one of those like full PDF documents.
Yeah.
Okay, yeah, I think that's fair. We can totally do that next time.
Thank you.
Yes. Abby, I'm glad that you thought it was helpful. Thank you. Caroline, can we ask about a question? Yeah, ask about a question. Yeah, Caroline, what's your question real quick?
Can you hear me?
Yeah, I can hear you.
Okay, cool.
Here, let me see if I can, you can share your screen if you want to.
Sure. It still says disabled. I think you'll have to just switch it.
Okay. Maybe that's better. Try that again.
Perfect. Here. Oh, wait. Okay, just kidding. It says regraded, so I'm not sure.
Oh, you must have went back in there and changed it. It might have been an issue.
Okay, but so it was greater then, because I was thinking, because like I already knew the pKa of alcohol, which was greater than the pKa of like phenol, so that's why I put that answer. But was that right?
Question 1 second. It says the bolded hydroxyl group in cell sept is part of a phenol function group. We would expect the pKa of the hydroxyl group shown to be greater than or less than the pKa of phenol. The pKa of what? The pKa of the hydroxyl group? Oh, here?
Yeah. I mean, yeah, it says the bolded hydroxyl group.
Okay. It's greater than is the correct answer, and that's probably why you got your 2 points back. And the reason that is remember that whole thing we talked about of like that substituent being either an electron withdrawing or an electron donating group. And clearly, since that I'm looking at this OCH3 group that's attached to that ring as well, the benzene ring, that oxygen atom has lone pairs. So when you donate via resonance into that benzene ring, it's repulsive. It's not a good thing with that negative charge on the oxygen. So yeah, it would be a destabilizing kind of trend. And that would make the pKa greater, which means less acidic. Yeah. So it looks like you got your points back already.
So so the base would not be as stable because it's giving electrons into benzene that's already really stable?
Well, yeah, so that last part was kind of wrong. Like, imagine, remember, that's O minus, that phenol, when that H goes away.
Right.
So that's already negative. So then when that OCH3 group, like that substituent, donates electrons via resonance, you're adding more negative electrons to an already negative oxygen atom. Does that make sense? Like you're putting two negatives close to each other, and that's not good, if that makes sense.
So the other... Okay, wait, sorry. Can you say that again?
Sure. Yeah.
Sorry.
So again, like I can't really draw it, but yeah, put your mouse where the OCH3 is. Nope, to the left, up, right there. Yeah, that group. Okay. Those lone pairs on that oxygen can donate into the ring. Okay, so electrons are negative, right? So you're pushing those in via resonance. But remember, the whole point of like acid base stuff is like that OH that you see right below it. If you want to put your mouse there, go down right there. That's O minus when the base comes in, right? You know that?
Right.
That's O minus. So the negative electrons that are pushed in via resonance come close to that O minus, and that's repulsive. That's like not a good thing.
Oh, so the ones that come from here are pushed close to here?
Yep. and that's
So
a destabilizing thing, which makes it not stable. Yeah.
okay, because I was thinking it was just asking like literally like the pK of, because I was thinking of the pK of alcohol versus the pK of
Oh,
phenol.
like the number? Yeah.
Yeah.
So no, actually, this isn't even talking about the pKa of an alcohol. This is like this functional group, like this whole cell set structure versus just a plain phenol, if that makes sense.
Oh, I guess because
Yeah.
it said the bolded hydroxyl group, which is just this part. So I was like, okay.
So yeah, so remember, when that hydroxyl group is attached to a benzene, it's phenol and not just an alcohol, if that makes sense. So it's yeah. I
Okay,
think you just
that
read the
makes sense.
question kind of wrong, but yeah, you still got the points right, so that's good.
Okay,
All
thank
right.
you.
Yep. All right, so let's go back to, let's do this. Joshua, do you have a question you want to ask?
Yeah, but mine was just number 11. I was just kind of confused between answer 2 and 3.
Can you share your screen, because I don't have it.
Yeah.
Yeah,
Okay.
hold up. Thanks. All right.
Can you see it or no?
Yep, I can see it. So it says rank the following molecules, ions, in terms of their basicity. Was this the question I was looking at? No, this wasn't the dialogue. Okay, so you're confused with 2 and 3. You got them flipped.
Yeah.
How do I read this? Okay, answer 1. So it should be C is the least basic, and then D is more basic. Okay, so C versus D. Okay, so I see the issue here. Like, both. Okay, so you thought D would be better than C.
Yeah, because
and the reason, the induction, is that what it is?
Yeah, the 3 Fs, yeah.
Okay, so what the bigger issue here is, once you resonate, what happens to that negative charge? So at first, for C and D, they're both on carbons. You see that, right, to start.
Yeah.
But when you resonate all the way to the left of both of those structures, you get a negative charge at some point on either an oxygen atom or a carbon atom. And that was the all-time factor. Do you kind of see that?
Oh, okay.
Yeah. So it
okay.
was an O minus versus a C minus, even with the fluorines there. And since the O minus is better, that's why. It was more stable, which is more acidic. So it should have been, where am I looking? D should have been.
Yeah.
Oh, I see. I just said what you put. Hold on. So it should be flipped. C is lower than that. Yeah. Okay. So it looks like, even though there's resonance possible with both of them, and you get that negative on a carbon, the induction with the 3 fluorines makes it even better. Okay. So I can explain that again. Like,
Okay. Yeah,
because,
wait, wouldn't that mean it's more acidic then? Or no?
Yeah, so do you see what you put? Like, it should be BCDA, and you put BDCA. So since D has induction as well as resonance, it should be where you put C, if that makes sense. It's a little bit better than this. I can't like mouth over it. Here, can you put your mouse on D?
Yeah.
Okay, cool. So that structure that we're talking about, yes, once you resonate, you get a negative charge on the carbon, but also because of these 3 fluorine atoms, that's really, really good, because it's pulling that negative charge even more across the molecule. So that makes it more stable, which means it's more acidic. Okay. Yeah. So, but in C, this one, when you resonate, you get a negative charge on the oxygen, which is really good because that's more electronegative, a lot more electronegative than carbon. So that is more stable than D, which means it's more acidic than D, which means it should, yeah. Does that kind of make sense?
Yeah, okay, that makes sense.
I think it's confusing because the least and the most, like, that kind of gets confusing. Like, you should have wrote it as acidic all the way to the left and basic all the way to the right, and maybe that would have helped you. Yeah.
I mean, I think, because for this one, and am I allowed to ask one more or no?
Yeah. Why not? Yeah.
I think it was the next one. It asked which one was more basic. So for the first one, I thought
this is the question I was talking about that I thought was pretty tough. Yeah.
I was kind of confused because I thought it was based off which atom is connected, like which one's the more electronegative one. Or
looking at, Okay. So which pair of molecules would be the most basic? Yeah, so again, it's that substituent effect that we kind of already talked about. So you could pick any proton in structure A or structure B. You could pick the ones on the benzene. You could pick the ones that are like on this I guess this other pi bond all the way to the right. You know where those two oxygens are. So any of those protons, you could kind of argue that they're equivalent. And once you depronate that and you have a negative charge, what does this substituent do? What does that substituent do in the sense of like, does that OCH3 group or that nitro group, what are they doing? And the nitro group doesn't have any lone pairs. It's electron withdrawing. So it's basically pulling electrons across the whole ring and it's spreading it out. Whereas in A, you're donating those electrons from that oxygen atom into the ring, adding more negative charge to an already negative thing. And that's repulsive. That's not good. So since B is more stable, it's more acidic, and you picked B. It should have been the opposite. Does that make sense?
Oh, okay, that makes sense.
Yeah.
Okay, yeah.
Yeah. Okay, happy that you got that though.
Yep, appreciate it. Thank you.
Yep. Caroline, because there's one I missed that I don't see. Oh, sorry, hold on, that just went away. What'd you say? Because there's one.
That was from earlier.
Oh, okay.
I did have another one, but if you would rather me ask it at the end.
No, because nomenclature is going to be really quick. Nomenclature is going to take me like 15 minutes. So, yeah. What do you want?
Is it okay if I share my screen?
Yeah, do that.
Okay, also, because we were already on this one, like I got it right, but I just want to go over it again if that's okay. So, so for A here, I remember like we did that example in the workbook, and this was like the electron donating curve.
Yep.
And so that makes it less
stable, which means it's more basic.
Oh, because more stable would be weaker.
Correct. Yeah.
Right.
I'm sorry. More unstable would be weaker. That's what it was. So because remember that whole donating via resonance, you can. Here, let me draw it. Can you guys see my paper or something?
Yeah.
As well. Okay. So let's just show that again. So I'm talking about, and I don't know, let's just say it's this proton and the rest of the molecule, and versus it's a nitro. So this is important. It definitely is gonna come up again. So O2N. So remember that Lewis structure of O2N was that. Please remember that. So there's no lone pair, so that's electron withdrawing group. So what happens is once you get this negative charge with a base, like this is gonna pull like electrons out, like it's an inductive group. Like there are no lone pairs to resonate with. You know what I mean? So this is basically equivalent to saying it's like fluorine or something. So that's
because it doesn't have, so because the nitrogen doesn't have any lone pairs, that's better?
Yes. Because it's basically equivalent to saying that it's inductive, so it makes it more acidic. Does that make sense?
Okay.
I don't think you like me on that. Hold on.
I mean, I guess because like, so I know you said for fluorine it's different. Like even though it has lone pairs, that's what it likes.
Yes. Yeah. So remember, like I said, it's a weird thing, and you'll see that again in Orgo too. Like although fluorine does have these lone pairs, halogens are so electronegative that they are not going to give them up at all, and that should make logical sense. Like that just makes sense. So that is kind of the exception, but. In terms of inductive effect, what we really see is like, when we see like a negative charge and we see like a fluorine, that's induction. That's the classic example of what we see. But this was kind of an application of that with this substituent. That nitro group doesn't have lone pairs. It's not going to donate any electrons into the ring. That won't happen. So we're not going to have any of these electron-electron repulsions that we see here. Because when we get rid of that, proton and we put a negative charge, these resonate in and we're adding electrons, and that's not good. Do you see that?
Okay. Yeah, I see that. So because we're adding in electrons, that would just increase the amount of negative charge that's there and make it unstable. And having both of the unstable is a stronger base.
Exactly. You got it.
What about for the like C and D and then E and F?
Let me see.
I drew for E and F, like I drew the conjugate acid and it'd be more stable with like the nitrogen having the positive charge, so I figured that'd be more basic if it produces the better acid, right?
Let me think about this one. It's tough. see. Let me think about a lot. Honestly, I don't really know how I would do this one. C versus D. What did you do? You
So I
pronated the
drew.
nitrogen in both?
Yeah, I pronated nitrogen in both and drew like resonance for the conjugate acid, and I'm pretty sure there was more. Like it was better for C, so that's why I picked it as more basic.
I think
I don't know if it has to deal with like an inductive or withdrawing group because the oxygen has like 2 lone pairs. I didn't, or like it being closer or farther away. I didn't know if that.
That's exactly what it is. So when you
Okay.
protonate, so everyone who's listening is confused. For C versus D, like you're going to protonate the nitrogen over the oxygen for obvious reasons. The oxygen is more electronegative, so it doesn't really want to give off its electrons, whereas the nitrogen is less electronegative and wants to give off its electrons to a proton or something like that. So in both structures, you get, something that looks like that protonated, and you get that protonated. And I'm just going to draw these circles to indicate it's benzene. And then, you have the difference of that there versus this there. So when you do resonance, you'll eventually get a positive charge on the oxygens of both of them. Like that's true. But when you do that, you can see how since this nitrogen is closer, it's inductive, even though it's a positive charge and not a negative. So it's inductive closer, which means this is more stable, which means it's, more acidic. And that's the logic, since, C would be more basic than that.
Wouldn't it be less stable if that nitrogen has a positive charge as well? So then it's like 2 positive charges closer to each other?
Well, they wouldn't both have the positive charges. It's like after you resonate, you end up getting a positive charge on that one. Does that make sense?
And so why would having that closer, because nitrogen
it's pulling.
would have a
the
lone
nitrogen
pair?
is, yeah, well, here, let me draw out the resonance structures. Maybe that's helpful.
Yeah, thank you. Sorry.
No, you're good. So it would be, let me just draw this out right. So it would be this, that, and it would be this. Okay, so we're positive here. Okay, so eventually what you can do is you can resonate these in, push these around, and we can get there. So that's the resonance arrows I did. And the resulting structure would look something like this. Oh, I guess it's still a positive charge. Okay, but you could also still, this is still a valid move. Let me push those electrons out. And then you get something like this. Again, I thought this was pretty hard. Like, I'm not even gonna lie. I thought this was tough.
Okay, yeah.
So we're there. Yeah, so we're there, right? This is the resonance structure we got. So this group, like at this point where it's at in terms of the resonance structure, is just inductive with respect to this, okay? You can't, do you see how, can these nitrogen lone pairs like donate anywhere into the right side? No. So for the purposes right now, this is inductive. And since it's inductive, it's pulling that charge over the ring closer. And the same thing's gonna happen with this guy. It's just farther away. So it's less stable.
I think I drew the resonance structures for the the conjugate acids, and then C had more
of a,
if whichever, I remember one of them had more, and then if there's more resonance, doesn't that make a more stable?
Well, no, so that's actually not right. So they both have the same degree of resonance.
Okay.
They both do. Yeah, so you might have done something wrong with your resonance structures. They both have the same degree of resonance. Like, I know that 100%. I think it was just the positioning of that substituent made it more stable for D, if that makes sense.
Okay, because when you resonate it, it would have. Okay, that makes sense.
Yeah, I know it's not the greatest.
That's okay. The other thing was
you got really choppy. I didn't hear what you said. Can you repeat that? I didn't really hear what you said.
Sorry.
You're good.
Can you go over this one if that's okay?
Yeah. So scroll up a little bit. I can see the directions. Remdesivir. Okay, this is funny. Remdesivir is what you've been hearing about a lot in the news. It's the antiviral that is allegedly capable of treating COVID-19. And I say allegedly sparingly. So we're ranking these in terms of acidity. So it looks like B you thought was the least acidic. Okay. because, okay, so the first thing is erase those H's and put a negative charge, right? So you see carbon a negative, which is B, which is why you probably put that as least acidic. And then you see you have 2 negatives for the nitrogens. Okay, so that's good. And you said that C would be the most acidic. And in actuality, it is, okay. So it comes down, let me plot my periodic table, if I can find it. Oh, where'd it go? Oh, here it is.
I think I put it because for C, like it could resonate, but for A, it couldn't.
That's not true. Okay, so if you look at A, where that kind of amine is, see that phospho group?
Yeah.
You can resonate up
you
over
can,
there. Yeah.
Yeah,
Do you see that?
you can. Yeah,
And
I
that
see
phosphorus group is, that
man.
phosphate is bigger. It's a larger, if you look at the periodic table right here, phosphorus is bigger than nitrogen. So it's better at accommodating any charge, if that makes sense.
Oh, so like if you think about it, it would really be phosphorus and nitrogen with a negative charge versus 2 nitrogens with a negative charge.
Exactly.
And so that makes it more stable, which is a weaker base and more acidic.
Exactly. Yep.
Oh man, I can't believe I'm.
It's okay. It's okay. You know,
Okay.
it's good that you caught that. All right. Let's see. I want to do Josh. Is this a new question for 14, or you're just kind of talking to Abby?
I was just kind of talking to Abby.
Okay.
I'm so sorry. Did we go over 13 or no? I think that
I
was
don't
just
know. I'm not really looking at the numbers. Did we go over 13?
I think it was just resonance,
No.
but I'm not sure that for the first one.
You can share your screen if you have it, and I can see.
Yeah.
I don't have it in front of me.
Oh yeah, this button, then that button.
Yeah, we didn't go over this one yet.
Okay.
Would it be A because of resonance?
Let me read this one. For each molecule in molecule 1 and molecule 2, determine which level proton will have the lowest. Okay, so lowest pK you knew is the most acidic, right?
Yeah.
Okay, so you thought it was B.
I think I tried to draw it out, but maybe I drew it out wrong.
Oh my God. Let's see. Okay, so if you were to deprotonate that H, you get a negative on the nitrogen. You move it into the ring. You get a negative there. Okay, if you get a negative there, let me just see. You put that in, push that in, put that in. Nitrogen. Okay, you do that one. Okay. Yeah. So I think it comes down to these resonance structures. I have to draw them out, honestly, because I did them in my head, but I'm not sure if that's exactly what it is. So NH2, NH2, CN. So CN, I'm going to abbreviate as this. Shoot, did I do that right? CN, that's an N. Okay, so that's the bond. Okay, so let's just do what happens if this was the A one. Okay, so erase the H, put a negative. So I'm going to do this move, this move, this move, and this move. Okay?
Mm-hmm.
So that results in this structure. NH, is it NH plus? Is 2, 3, and 1 lone pair still? No, it'd be plus, yeah. Okay, and then you have this, you have this, you have that, and then you have that. Okay, so that would be from A. Let me do the same thing for B and see if I get a different structure. Okay, so if you scribble that out, you put a negative, you push it in, it goes here. Okay, so I can already see the difference. With this for A, when I do this thing with A, I get a negative charge on a nitrogen. Do you see that at the end right here?
Yeah.
When I do this one, do you see how there's no way that I can push these electrons to play with this nitrile?
Yeah, okay, that's what I thought it was.
Yeah, because all of these contributing structures are going to be negatives on carbons, but this one's going to be a negative on a nitrogen at some point, if that makes sense.
Gotcha, no, I understand. I think I just drew it wrong.
Yeah. Okay, but yeah, good. I'm happy that you got that. And I think, did somebody want another question? Do you want 16? Still, I don't know.
Yeah, that was me for 16.
Okay. Can you share your screen if you have it on? Hold up, and then
Sure.
we'll switch over.
Do you see it?
Yes. Okay, go down a little bit. Yeah, let's see. Equilibrium, answer
Yeah.
1. Okay.
Like, I don't understand why I got it wrong. Like I did the whole equilibrium thing, but I don't know why I got it wrong.
Let's see. So deprotonated nitrogen would be the right side. And then you would get a negative nitrogen on the right. Let me look at my periodic table. I would have picked the right too.
Okay, well, okay.
You're like, thank you. Let me see. Because what I'm looking at is conjugate-based stability. So like for me personally, I see, and I could be missing something, but there's that, and then this is LDA. This is a very common base. And when you get that, you get something like that, right? Can you see this?
Yeah. Mm-hmm.
Yeah. So I'm comparing this conjugate base with this conjugate base, and we have a negative on a carbon versus a negative on a nitrogen. And I know that this is more stable, so I'm thinking shift to the right.
Exactly.
But let's see, I think because there's one, Caroline, because there's one I missed that I don't see how it's wrong. Also, oh, different question. Okay. Yeah, I'm thinking right, unless I'm missing something here. Yeah, I don't know. I really don't know. I wish I had a better answer for you. Maybe I would ask Dr. Peterson, and it might be, she's going to post a most missed worked out solutions for you guys. So maybe this will be on there. So give it like a day or something. I really would say right, to be honest.
I put what Abby said, like the same reason that Abby said in the chat.
Because the pK of the alkene versus, you guys memorized them? Is that what it was?
Yeah.
Okay, so yeah, so that would have, my bad, alkyne. I didn't even notice. Yeah, so it probably does come down to that, knowing the pKa's. Again, I told you I don't memorize pKa's because if it was like a 2-pointer, I'm willing to like miss the points on that. But again, I would have picked right, to be completely honest with you, if I didn't, because I don't have the numbers memorized. Yeah.
Okay. No, it's okay.
Yeah, I'm sorry. I know that's all I got.
It's okay. Well, thank you.
Yeah, see, Abby says the same thing. Abby was like, I missed it too because they didn't memorize them. That's okay. Like if it's 2 points, it's 2 points. All right, so let's jump back into, I want to start doing some of this other stuff, this new material. And it's pretty easy. To me, I hate this stuff. I think it's so boring, but like it honestly is like a free couple points on every future test all the way up through Orgo 2. You're going to have some nomenclature questions. And essentially what that looks like is as we get more and more functional groups, starting in chapter 6, like we'll start with alkenes and then alkynes, you're going to learn how to name each of those functional groups. And it's a little bit, they all follow the same rules, just slightly different. Okay. So the first thing that you want to do with this, parent chain is find the longest carbon chain. So longest carbon chain is the most important thing above all. Okay. And then after you find that longest carbon chain, you want to number it in a way such that these substituents, and we'll talk about what a substituent is, gets the lowest possible set of numbers. So number in a way to give lowest numbers. Okay. And then I think we can just start there. So for this guy, for A, we see that we have, 1, 2, 3, 4, 5, 6, 7, the 7 carbon chain. Okay, and 7 gets the prefix hept, and I think I should talk about those prefixes in a second. So hept is the prefix for 7, okay, and then these are all alkanes. So for now, everything is going to end in ane, okay, A-N-E. So you would do hept, ane, pretty easy, okay. And again, where do I get these prefixes from? So I say it really fast: meth, eth, prop, bute, pent, hex, hept, octanone, dec. That's how you guys should say it, okay? Meth, eth, prop, bute, pent, hex, and that's literally how I say it in my head. Pent, hex, hept, octanone, dec, okay? And that's 1 through 10, okay? So based on the number of carbons for that parent chain, it's either meth, eth, prop, bute, pent, hex, hept, octanone, dec. I know that sounds crazy, but like if you say it over and over again, you'll get it. What was the first test the easiest one? I think 1 and 2 are pretty equivalent, if that makes sense. So if you did pretty well on 1, you'll probably do pretty well on 2, because like the same types of materials-ish, give or take. Was the first, oh yeah, okay, cool. Thanks for that. All right, so that's heptane. So then look at this one. So it's 1, 2, 3, 4, 5. So 5 is pent, so pentane. Okay, you guys are getting it, the formula. Okay, and then here, okay, so longest carbon chain. So I see maybe 1, 2, 3, 4, 5, 6. I see 1, 2, 3, 4, 5, 6. Yeah, so it seems like 6 is going to be like the longest carbon chain. But now I want to number it in a way such that I give the substituents, so anything that's coming off that main chain, the lowest set of numbers. So, you know, it doesn't make sense for me to start here, and that'll explain in a second. Okay, because then that substituent or this methyl group is 5. And I could do it in a way in purple, where it's 1, 2, 3, 4, 5, 6. Do you see that? So clearly the purple numbering would be better. Okay, so now that we have all of that, we have that numbering scheme laid out, we have to name the substituents in front of the name. Okay, and that makes sense. It's kind of like just indicating where everything is. So where is this methyl substituent? Well, it's on carbon 2. So we're going to say 2 dash to indicate like what that substituent name is, methyl. Okay, so on 2, there's that methyl group. And this was what type of structure? It was a hexane. So hex is 6, and it's an alkane, so hexane. Okay, so this is on the carbon 2, there's a methyl, and it's a hexane. Okay, so it should logically make sense. So you always put the substituent names in front of the parent name, which means hexane, and you're going to always have the number to indicate what carbon that substituent was on. Okay, anybody have any questions up till now? 2-methylhexane. Okay, so again, same thing. So we're going to see what's the longest parent chain here. So maybe 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4. It usually seems like 5 is the best one. Okay, so then should I number it from left to right or right to left? And put it in the chat. Let's see, left to right or right to left? Left to right, yeah, left to right, because we would give these substituents, these 2 methyl groups, the lower set of numbers. So 1, 2, 3, 4, 5. Instead of 1, 2, 3, you give them 4s, okay? But we want to give them 2s. So when we have more than 1, you would just, it's kind of redundant, but this is what the rules are. It's 2, 2 to indicate that there are 2 of them, and also redundant. Since there's 2 of them, use prefixes to indicate how many. So di, okay? Di for 2, and what are they? They're 2 methyl groups, dimethyl, and what was this? This was a pentane, so dimethylpentane. Okay, so a little weird. I think this is very redundant, but it's just the rules. You don't ask me why they are. Someone made them up, but it's 2, 2 to indicate that there are 2 methyls, and you use commas, and then what were they? Well, it was dimethyl. Okay, cool. All right. So then you can see that it gets a little bit more complicated. And again, the first thing you always want to do is just find a longest chain. So maybe I'll start here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I got 8. What if I started here? 1, 2, 3, 4, 5, 6, 7. Nope. 1, 2, 3, 4, 5, 6. No. Okay, what if I started here? 1, 2, 3, 4, 5, 6, 7, 8. Okay, it seems like no matter what, I'm going to get 8. So I can either start from, here, I can start from here, or I could start from here. Okay, so which one do I want? Well, if I start from here, my first substituent will get a 2. Do you see that? I get a 2 on this methyl group. But if I started here, my first substituent isn't until 3. And same thing for here, it's a 3. Okay, so I think that this one's probably the best one, and I'll do it in purple. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so half the battle is really getting that numbering scheme down. And this is the best one because, yeah, there are multiple different ways that I could have numbered it to get 8. So then the next thing I want to think about is number it in a way to give me the lowest set of numbers. So yeah, I could get a 2 here versus the 3s going on. Okay, so, you know, this structure would be, so we have to think now, now you have to alphabetize. Okay, so there's just so many different rules, but they all make sense and you only get better with practice. So on 3, 2 carbons would be ethyl, an ethyl group. And again, over here on 4, it's another ethyl group. And then on 2, we have methyl. So what I do is I write M, E, and E, just to like kind of tell me what I have to do alphabetically. So clearly E becomes before M. So I have to say 3, 4, okay, ethyl. Okay, so there's 2 ethyl groups, and then 2 methyl octane. Okay, does that make sense? So we alphabetize now. So 3, 4, there's 2 ethyl groups. 2, there's a methyl group, and then octane. So 8. Yeah, go for it, Caroline. Caroline or Caroline? What? Just correct me on that.
Caroline.
Caroline.
It's Caroline. Yeah.
Yeah.
If we started from the one where you put the E.
Okay. Well, there's 2 E's. So from this one or that one?
Oh, sorry. The one where the 3 ethyl group.
Gotcha.
Yeah.
Right.
So
Yep.
so that E. So that E to the left, if we started there, wouldn't we just, like, wouldn't there only be 2 substituents then? Like, would that be better than 3?
So it doesn't matter, like, the number of substituents. So it just matters that you give the substituents encountered first the lowest set of numbers. Like, that's the verbiage in the IUPAC rules. It's the substituent first just has to be the lowest set of number, if that makes sense.
What would if we did start there, what would the group on 3 be? Like the one?
Isopropyl.
Isopropyl, okay.
Yeah, so you're talking about this one down here?
Yeah.
Yeah, that would be iso. And we'll talk about those common names in a second. Yeah.
Okay.
So
great,
that's
thanks.
actually, I think I know what you did. That's a very common trick. Like, people see that one of those common structures, like here, you would think maybe tert-butyl, and people just number it based on that to give maybe isopropyl a name. And that's not true. It's a big, and we'll see those in a second. So I'll get you.
Okay, thank you.
All right, so keep going. So on F, we got to find that longest carbon chain. So maybe a 1, 2, 3, 4, 5, a 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Oh, okay. Did you see that? So I have either 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Okay, so it doesn't matter, it seems like, where I do it, because if I do it left to right or right to left, I'm still going to get the same numbering scheme here. So let's just pick this one. So that's 6. And on 3 and 4, I have 2 methyls. So I would call this 3, 4 dimethyl hexane. Okay. Pretty easy. And even if I did it this way, I would still get the same thing. Okay, so for this guy, it looks like there is symmetry. So it doesn't matter if I do left to right or right to left. So let's just number it. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. So yeah, so 9 seems to be the best one. Okay. So it looks like 4 is going to be a methyl. 6 is going to be a methyl. And 5 is going to be 1, 2, 3. So a 3 carbon is propyl. Okay, that propyl. So this would be P. So LMNOP. Okay, so M comes first. So that would be 4, 6 dimethyl. Where am I? Dimethyl. And then 5 propyl. So 5 propyl. And 9 nonane. Okay. So 4, 6, there were 2 of those methyls. 5, there was a propyl, and then a nonane. Okay. Again, you just get better at practice, honestly. Okay, so let's move to the next one. So where is the longest carbon chain? So maybe I'm starting up here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, maybe here. 1, 2, 3, 4, 5, 6, 7. No. Maybe 1, 2, 3, 4, 5, 6. Maybe 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I see 8 seems to be like the biggest carbon chain. And I could, it doesn't matter which way I do it. Again, because it seems like you're going to get the same answer because of the symmetry. But let's just do that one. And it looks like on 3 and 6, I just have 2 methyls. So I'm going to do 3, 6 dimethyl. And that's octane. Okay. And I think that's good. All right. So let's just do an example of a ring. So we're going to look at J. So this is interesting. So we want a number around the ring just to give the lowest set of total numbers to all the substituents. So let's say I start here and I do 1 and I get 2, 3, 4, 5, 6, 7. So my substituents overall have a 3, 4, 5 and 7. So 3 plus 4 plus 5 plus 7. So that's going to be what, like 19? Something like that? Mental math? I don't know. 19? And then let's do it the right way. So the right way would be 1, 2, 3, 4, 5, 6, 7, 8. Okay, maybe that makes more sense because now my substituents have 1, 2, 3, and 5. So what is that? That's going to be like 11 or something like that? Yeah. So 11 is way better than 19 for reasons I just proved. So you want to just number it where you give this ethyl group 1. Okay. So that would be an E, an M, an M. Okay. And then this substituent is going to be a common name that you should know. Okay. And this is isobutyl. Okay. So if I wanted to do this, that's I. So it's E, I, and M. So it would be 1 ethyl, 5 isopropyl, 4 comma 5, I'm sorry, I'm using the other numbering, 2 comma 3 dimethyl. And then instead of just being octane, it's a cyclic structure. So you say cyclooctane. Cyclooctane. Long name. 1 ethyl, 5 isopropyl, 2, 3 dimethyl cyclooctane. Call your parents and say that to them. I learned how to name that structure. They'll be like, wow. Okay. Caroline, is that an old question or we did that already?
No. Okay, so if you started on the, so is it isobutyl or isopropyl?
Isobutyl. Isobutyl.
Okay.
And we'll talk about the difference in a second. Yeah.
I think you wrote isopropyl though.
Did I? Oh my gosh. Oops. See, I wrote isobutyl up here.
Okay.
Thank you.
But if you started on isobutyl, wouldn't you also get 1, 3, 4, and 5? Oh wait, no. And it'd be
no, yeah.
Oh, I see. Okay.
Yeah. Cool. Yeah, there's always going to be one right way. You're not going to have like, multiple right ways for these.
Okay, thank you.
Yeah, and okay, so I'm still kind of confused. What are you confused about?
I think just like the numbering and like, I think that's mostly what I got. Like
how to number it right? Okay.
Yeah.
So you can pick whatever carbon to start. Like, look at the purple. I literally was just like, let me start here. Why not? And I just went around the ring. You have to go either clockwise or counterclockwise. It literally does not matter. It's whatever you pick. So if I chose to number it like this, I get an ethyl group on 3, a methyl on 4, a methyl on 5, and a isobutyl on 7. And if you were to add up all those numbers, you get 19. Okay, but let's do it the right way. The true way is the red one. And you see you get a 1, a 2, a 3, and a 5. So when you add up those, you get 11. And the IUPAC rules established by these organic chemists like decades ago says that you name a molecule so that you give these substituents the lowest set of possible numbers. So 11 is definitely better than 19. So we want to do it this way, okay? That's just like the way that they say it, like the guidelines. There's no real theory to this. That's the way that it is.
Okay.
So you get that, right?
Yeah. I think I got confused. I didn't know if you were like adding up like the total number. I don't know. I get it now.
Yeah, no, the number doesn't mean anything just except for the fact that like, oh, like how do I know that my numbering is right, if that makes sense?
Yeah.
Yeah.
Thank you.
Okay, good. So let's go over real quick those gotta go. Okay. See you, Abby. So another thing that, it's these common names, okay? And let's just talk about those briefly. So you have a couple of them. So you have this one. You have this one. You have this one. You have this one. I think it's that, right? Okay, and I'm trying to think. You have also, and I'm going to draw this one. I kind of want to draw it under here. Okay, so these are like the 5 I think you need to know. So let's talk about that. So this one, the Y, okay? The Y is isopropyl, okay? So that's kind of like how I always remember it. Isopropyl alcohol is like probably something you've heard before organic chemistry, okay? So this is actually like used to clean like acetone. I mean, it's used in some acetones, like the mixes to like get rid of nail polish remover, glassware, things like that. So this is isopropyl alcohol. you know what an alcohol is, OH, and that's an isopropyl group. Okay, so that's isopropyl alcohol. That's kind of what you use. Squiggly just means the rest of the molecule. So like you could have, see how over here I put OH, like anything attached, you can put OH, you know, or more carbons, or, but isopropyl specifically is anything above the squiggly. Okay, so this one carbon with 2 other carbons attached. Does that make sense? The squiggly, just the rest of it. No, it's not 2 carbons on each side. Here, maybe R for rest of the molecule, That makes sense.
And then like on the sides of like the squiggle, like those aren't, that's not meant to be like a carbon. You know what I mean? Like you drew that.
Oh, here and here? No. Yeah, those are not. Yeah.
Okay.
The squigglies. Yep. Okay. So for this guy, it's isopropyl. Okay. And the way that I remember that is like, why? I don't know. It just screams like, why did I drink? Like, I don't know, like isopropyl. So maybe that helps you. Why did I drink so much? Isopropyl alcohol. Maybe that helps you. Okay. So that's isopropyl. Then this one looks like isopropyl, but it just has 1 extra carbon in between. You see that? They just add an extra carbon. So it's not isopropyl, it's isobutyl. So similar names, but isobutyl. And why is it butyl? Well, butyl we know is the prefix for 4. So I better have 4 carbons here, right? 1, 2, 3, 4. All right. So the names make sense. Propyl, 1, 2, 3. Okay. And they're iso because they're different isoforms of each other. Whoa. Can I, yeah, you can ask something. What's up?
Sorry, I just missed him.
You're good.
Okay, so do you mind drawing it without the R group attached so I can see, so like either one of those?
Sure, that's isopropyl.
Okay, so there's not like another, I was thinking there, you know, I thought it was like the actual Y, so there would be another like methyl on the second one, but it's not.
It always will look like a Y because this is like the bond that it's attached to. Does that make sense? Like you could have a benzene here. Like, you know, that like, it's just, you're always gonna look like a Y because there's some sort of connection between this isopropyl group and some other thing, benzene. So it always looks like a Y, but it really is that. That makes sense. So here, like the same thing. That's the isopropyl group. This is the alcohol group.
Okay, and then I guess I'll just go through an example probably of like what it would look like in a molecule, bigger one.
Yeah, we'll get there.
Okay, cool.
Keisha, you have a question? I see your hands raised.
Yeah, so can you go over again why? I understand why it's propyl and butyl because the carbon, but why is it iso?
Okay, so iso just means like an isomer, and we haven't talked about isomers yet. Isomer means like it's like the same kind of like structure, but differs slightly. So iso is a prefix that means kind of similar, if that helps.
Okay.
We'll get there with the next chapter. We're not there yet though.
Okay.
But good question. All right, so this one looks like a chicken foot. I don't know. That's how I always ask that. Leah, 1 second. So yeah, so I always say like this one looks like a chicken foot, and I don't know how to really remember this, but tert-butyl is the name. Tert-butyl, and notice the hyphen. I'll talk about what that means in a second. So tert-butyl is the chicken foot, and this one looks like tert-butyl, but it's neopentyl. Neopentyl. Okay, and it's neopentyl because it's 5. So 1, 2, 3, 4, 5. And neo, because I just think it's the new chicken foot. It's longer, like it's evolutionary evolved. Like maybe it's longer with the extra carbon. So new, it's a new chicken foot. I don't know. Maybe that helps. I just give you like silly ways to remember it. And this last one. So why did I put this isobutyl under here? I mean, this structure under isobutyl. And this is the exact same structure. However, all I did was take this methyl group off, like this one off, and I put it here on that carbon. So instead of it being on, you know, maybe this like 3rd carbon, it's on the 2nd carbon or something like that. So I call it sec-butyl, the 2nd carbon instead of the 3rd carbon or whatever it is. Okay, so those are your 5 names. That's how I remember them. Maybe they help you. Isopropyl looks like isobutyl, except just an extra carbon. Tert-butyl is the chicken foot. Neopentyl is the newer version of the chicken foot. So not there's that one. And sec-butyl looks like isobutyl, just on the 2nd carbon instead of the 3rd. Okay, Leah, you got a question?
Okay, what I was wondering is I know for like when you do buy, try, and that sort of thing, or die and try, not buy, you don't include that when you're listing them in alphabetical, but for
Correct.
these like, isomers, you do take into account the...
Yeah, exactly. So I'm gonna highlight this for you. So I, B, B, P, B. Okay, so that's what you have to. Okay, bye Keisha, see ya. So that's kind of how you would do it. You have to look at the I's of these, or the B's. The T doesn't count, the N doesn't count, or the S doesn't count. Okay.
So
Yeah,
if
so
there's, oh, sorry.
you
If
can go.
there's a hyphen, then you take into account the second part of it.
Yeah, exactly. So for instance, let me do this. I'm just making this up real quick. Let's do, and let me do this one. Okay, sorry, one sec. Okay, so we see the structure, right? So if I give you this on the test, it's like, what do I need to do? So, okay, I can either start here to give this 1, or I can start here to give this 1. So it's either gonna be 1 and 3, you see that, 1, 2, 3, or 1, 2, 3. So let's say I did it this way. Okay, 1, 2, 3. So 1 would be isopropyl, okay, so I, and 3 looks like the sec-butyl guy. So that's B, okay? So it would be, so this numbering scheme actually doesn't make sense because you could have numbered it either way to make it equivalent. So the better one would have been, I'm writing on something else. 1, 2, 3. So now 1 is still sec-butyl, 3 is still isopropyl, but now the numbering matches. So it would be 1 sec-butyl, 3 isopropyl, cyclohexane. Do you see that?
Yeah, thank you.
Cool. All right.
I'm sorry to
You're good.
interrupt. Okay, so just to make sure I understand this, so basically we start the 1 on the butyl because B is before I in the
Exactly.
alphabet.
Yep, exactly.
Okay, so that just only works for those isobutyl, but like the ones we're doing before, it doesn't. Okay.
Okay, good. No, that's fine. Let's do it. So I put 2 methyls there.
Okay. Yeah.
Okay, so it would still be 1 sec-butyl, 3 isopropyl, 2, 2 dimethyl cyclohexane. So that's fine. You can still do that.
Okay, but what if you had like an ethyl group?
Okay, so then it goes in between A, C, D, E, F, G, H, I. It goes in between the sec-butyl and the 3 isopropyl. So you would do maybe like, let's do this. Maybe that was an ethyl. So it becomes 1 sec-butyl, 2 ethyl. So I can't really write that. I'm like running out of space. But it would be 2 ethyl, 3 isopropyl, 2 methyl cyclohexane. Do you see that?
Yeah, I see it.
Exactly.
But I'm sorry, just one more but what if like the ethyl group was like on the other carbon, you know, like adjacent to the 3rd carbon in the first example?
So here? Is that what you want?
Yeah, let's say it was there.
That
So
might change the whole thing.
I'm sorry, I was just
No, you're good. Yeah, you gotta think about this. Yeah. 1, 2, 3, 4. Yeah, we're not gonna give you this. Yeah, you
okay.
Yeah, then now it's too complicated. Yeah.
Okay.
But good question. All right. So yeah, so that's pretty much how you do nomenclature. So let me just catch you on an example real quick, maybe dealing with a common name. So let's do see any. Let's try practice doing the other way. I know we're about to run out of time, but that's perfect. You know, it's pretty easy topic. Let's do A and B. Why not? Because they both have common names. Okay, so I'm trying to think about where to start here. Okay, clearly I'm going to start on a substituent. Either I'm going to do 1, 2, 3 or 1, 2, 3. Okay, so for me, it makes sense to do 1, 2, 3 because you are going to get 1, 1, and 3. So that totals 5. Here, if you did 1, 2, 3, it would be 1, 3, 3, and that's 7. Okay, so we clearly like starting with 1. Okay, so up here we have a methyl, and down here we have the isopropyl. So we want to say for A, it's going to be 3 isopropyl, comma, or yeah, hyphen, 1, 1 dimethyl cyclohexane. Okay, so again, alphabetical. The numbering scheme was better with a 1 on the methyl because it was 1, 1, 3, not 1, 3, 3. Okay, and that's all I got for that one. So for B, kind of another thing with a common name here is we have, clearly, like just from looking at this, I'm gonna wanna start either here and going around, or here and going around, because you get two kind of substituents that are 1 and 2. It wouldn't make sense for me to start here because then I get 1, 2, 3, 1, 2, 3, and that's already worse. So this is methyl. And what's this one? So this one looks like isopropyl, but just a little bit longer. So it must be isobutyl. So I'm putting a B here. So for B, it should be, let's start here maybe. 1, 2, 3, 4, 5. So it looks like for this one, it is 1 isobutyl dash 2, 4 dimethyl cyclopentane. So once you guys do practice, you can see it's very formulated. It's like the same thing over and over again. But notice that is a common name right here. So in C, I think I see this isobutyl off the bat. And this is where most people get it confused on the test, is because they're going to start numbering it. So that they're like 1, 2, 3, 4, 5, 6, 7, 8, 9, or 1, 2, 3, 4, you know, something like that, left to right. And actually the correct numbering scheme for this is not left to right across here. There's a longer one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there's a 10 carbon chain. So it's a very, very common, you know, trick for us to show like these common groups coming off a long main parent chain, because people are very quick to be like, oh, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. But really there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So just always check every single avenue. I know it's always, and you think it's a waste of time, but it's always worth it in the long run. I think we are basically at the end of the session. And yeah, so we basically just have, I think that's it for nomenclature. Yeah, and you have all this practice to do, especially going backwards. And then on Monday, so just before we leave, just letting you know, so Monday, which is constitutional isomers and conformational isomers, or whatever that is by that time, this stuff gets very visual, okay? So if you have a molecular modeling kit, we're probably gonna deal with those on Monday. You don't need them. I have my own, so I can show you the models in person through Zoom, but it's very visual. So we're gonna do a lot of theory on Monday, probably a lot of theory instead of actual application, but you definitely don't wanna miss Monday. And yeah, that's it. I hope you guys are happy with your grades, and you can leave. And Caroline, you can stay and ask your question. And yeah, that's it.
The question is like kind of just advice, because
Okay.
I know like the model kit helps you like visualize it, but the reason I didn't want to get one is because like we're not going to be able to have a model on the exam, right? Like we can't have that in front of us.
Yeah, and honestly, this is the only lecture you will ever use them. Like
Okay.
for these next coming lectures, like you'll probably have them like 3 or 4 lectures coming up. Like they could help you, but number 1, they're expensive. You do not need them. And 2, like I'll have mine with me. So like I can just, basically what I'm doing with them is just showing you some theory and proving things to you. It's not like, you're not gonna be able to even use them on the test. So don't buy them. Yeah, that helps you.
Will you be able to like show us maybe like another way to look at it too, like without doing the model kits?
Yeah. I'm gonna, the models like is totally optional. Like I just do it to prove it to you again, but you don't, but they're fun.
Okay.
You know, again, you don't really need them, and I can show you them on paper too in 2D, as well. Yeah.
Yeah, that would, okay, thanks. All right.
Yep.
Thank you.
Cool. Yeah, Keisha, your question?
Yeah, so basically mine's not like a personal question, but mostly
Sure.
advice. So like obviously you love